Okay, everybody, this is section 2.6, last application, so Roman numeral 5. So we're finishing up our day 3, 2.6 here. We're going to look at some applications of rational functions. So looking at where asymptotes and those sort of behaviors can happen in real life situations. So I'm going to ask you to add this question. We're going to do a checkpoint example, which means it's one of the ones that there is a video for also in the textbook. So we're going to take a look at this example. It's a cost-benefit model. So looking at the cost of something versus the benefit. So when you're looking at economics and trying to decide, hey, is it worth it to do this? We look at how much it might cost, and then what benefit do we get from it? What value can we take from that? And if it's worth it or not. So being able to look at that is a great example, depending on the equation, the function of a rational function. So let's take a look at the scenario here we're going to look at. So the cost is what we're going to talk about, C, and notice it's in millions of dollars, of removing pollutants. So we're taking out pollutants out of a river. This is a really big issue with a lot of different communities that have to deal with pollution and trying to keep clean water system and all of that. We know we had some E. coli in the Hastings water system here not that long ago. So that's something that is kind of in the forefront of people's minds. So the cost of removing a certain percentage of industrial municipal pollutants in a river is given by this function right here. So if you can go ahead and get that function written down, notice it is a rational function. And notice the p-values that they're giving you for a domain. So the percent is between 0 and then up to 100, but not including 100. So think about percent. We can't really have more than 100% of the pollutants. But notice they don't even give you 100. And let's think about why that is. What would the domain of this function be? If you set the denominator equal to 0, it can't be 100. So when I take a look at my questions here, one of the questions I need to ask you about is it really possible to remove 100% of the pollutants? Well, according to the model, no, because if we do 100% of the pollutants, we'd be dividing by 0. So mathematically, doesn't really look like that's something that we can do with this model. We would hope we could take it all out, but the fact of the matter is you're probably always going to have some pollutant left in that water source. So looking at the domain of the function, I know we can't have 100 in there. So here's what the legislature is considering. They're considering a law that would require 90% of the pollutants to be removed. So oftentimes the way law is set is at different percentages. So we know we can't get it all out, but what are we going to require people to do? Currently the law states that 80% must be removed. So they want to up that to 90%. What would be the additional cost if they change the law? So from going to 80 to 90%, there's going to be some cost involved with this. So is it worth it? So that's that idea of cost-benefit model, so being able to do that. So how could we figure out how much more cost it would be for 90% versus 80%? Well, we have the function, so we can find the cost for each one of those. So let's calculate what those might be. So I'm going to go ahead and scooch down so we have some room. So how would we figure out the cost if it's 80%? Well, we'd be plugging in a P of 80 into our cost model. So 255 times 80 divided by 100 minus 80. So go ahead and do that calculation, see what the cost would be. So go ahead and type that in. Pause if you need to, see what that comes out to be. And check with my number. I got 1020. And remember, this is in what units? That's in millions of dollars. So that would be in million. So really, we're looking at 1,020,000,000. So it's a lot. That's the cost of what it is currently to do that law at 80%. All right, well, what would the cost be at 90%? Well, let's take a look and do that same calculation, but at 90. So we're going to go ahead and do that same cost analysis, but for 90% pollutants removed. So go ahead again, pause, or just type that in, see what you get. All right, and remember this is in millions again. So I got 2295, and that was in millions. So again, that would be like 2,295,000,000. So what is the additional cost? How would you figure out the additional cost to changing that law? Well, we need to find the difference between those two values. So we'll find the difference between at 90% pollutants removed and at 80% removed. And it looks to me, go ahead and check that, but I think it would be 1275, and that would be in millions. Or if we want to think about it, that would be $1.275 billion. So that would be the price tag associated with that. So what's the benefit then? Is it worth that benefit for taking that amount out and having that safe and clean water? So that would be the cost benefit analysis you'd have to do. Now, one thing that's kind of cool to look at is let's look at this graphically. We did this very algebraically, right? We have different methods of solving. Let's look at it graphically. So if you could go ahead and grab your graphing calculator, I'm going to have you type this equation in so we can think about it from the graph format. So go ahead and type in that equation. And again, make sure you have numerator and denominator so we can think about where those situations are going to be. And let's think about what the graph would look like. So we talked about the domain of the function, that we know we can't have a value of 100. So p equals 100 is an excluded value. And we know also then that that is going to be a vertical asymptote on the graph. So we have a vertical asymptote happening on the graph at x equals, or in this case, p equals 100. Now we're going to need to set up our window. So think about what's happening here for the window. So we're only going to go 0 to 100 because you can't have more than 100%. You're not going to have any negative values. So we can really be thinking quadrant 1. And if it were 100, if it could be, think about what that number would be. If you put 100 in the numerator, that looks like it would be at 25,500. So we need to set up our window so it goes up pretty high as well. So I'm thinking 0 to 100 going by tens, and then I put my Y max at 25,500. If it could actually go up that high, that's where it would be. So let's go ahead and graph and see what that looks like. So we have this first part of our graph, and again, the asymptote is happening at 100, which would be right at the end. So we have this rational function. We're not seeing the rest of it where the domain or where the values would be negative. Doesn't make sense in this situation to look at negative amounts of pollutant percent, so that wouldn't make sense. How could we do this question graphically? Would we be able to find these values on the graph as well? So how could we evaluate 80 and 90? Well, we could sure go to our table, right? So right now I have my table set going by ones, but how about going back to our table set? We could start at 80. Right? And I could go up by tens, even better, and then I can see what it would be at 80 and 90. So there's those two values that we came up with algebraically right in the table. So we could take out and look at the difference. Also notice at 100, error, right? Can't put 100 in. We can't ever remove 100% of the pollutants. Another way we could do, though, if we're just looking at the graph, you could trace, right? So we could look at the values. Right now I have it at x equals 90, and look, it's pretty close. It's not exact, but if I kind of trace back here and look at 80, can find the difference. It's pretty close, so you could get a good estimate anyway. So we could also look at this graphically. So always remember there's different ways to analyze data. So there's lots of different real-life applications that can be modeled with rational functions, and understanding what they mean and how we can solve is really helpful.